Good morning. Today we are going to discuss one last topic, that is polarization, and after that we will solve some problems. So I'll briefly discuss polarization, and then we will solve problems in a reverse chronological way. Um, um, go from what we have just discussed to and do some examples from previous concepts that we discussed. So when we were discussing the wave equation in the last lecture, we conveniently had chosen electric field to be along one particular direction, that is the y-axis, and the magnetic field to be along one particular direction, that is the z-axis. But in reality, for example, if you look at a ray of sunlight, in that sunlight, the electric field is oscillating every which way. It is not just along y-axis, but the electric field is oscillating along all directions. Such light where you have electric field oscillating along different directions without any preferred direction is what we call as unpolarized light. To choose the electric field to be along one particular direction, to have this electric field oscillate only along a specific preferred direction, would be polarizing light. So this would be an example of polarized light, in the sense that here you have electric field only along the y-axis, one particular direction. So unpolarized light has no preferred direction for electric field. It's oscillating along every which way. But in polarized light, you have electric field oscillating along one specific direction, which is the polarization direction, which is the direction of polarization. So electric field in polarized light oscillates only along the direction of polarization. So we have certain materials that are called polarizers. We have certain materials that are called polarizers that make this possible to filter out electric field from other directions and have electric field go through only one direction. This comes from the structure of the materials, as we had seen in the lecture where we discussed the origin of refractive index. When light is incident on a material, on any material, right? We saw how it polarizes electrically. It creates a dipole, oscillating dipole, where the electron oscillates and the proton doesn't, or the nucleus doesn't oscillate because it's heavy. We have discussed this while studying the origin of refractive index. And because of this, there are certain materials in which the material structure is in such a way that it lets only the electric field only along one specific direction go through. Such materials are what we call as polarizers. For example, if I have a polarizer, right, let's say that's like this, right, and let's say it's polarizing axis or polarizing direction is this way, right? Let's say this is the polarizing axis, and this is material itself is the polarizer. And if I have unpolarized light, that is light where the electric field is oscillating every which way, right, incident on this polarizer, right, if it is incident on this polarizer, then for any particular electric field, for example, if I choose this component of the electric field, right, say this is making an angle with the polarizing axis, say it is theta, then only a projection along this polarizing axis is let through. So if E is the electric field along this direction and its angle is theta with the polarizing axis, then only E cosine theta comes out. If I pick some other direction, say if I pick this direction, right, if I pick this direction, electric field oscillating along this direction in the unpolarized light, even for that, let's call that E prime, and let's call this angle theta prime. Even for E prime, only E prime cosine theta prime comes out, whatever is this angle. This angle may be different. So this angle may be different, theta prime. Right. So if I pick, say, one particular polarization, let's say E, one particular electric field in unpolarized light. This is unpolarized light that is incident. And in unpolarized light, as I have mentioned, you have electric field oscillating along every which way. So if I pick electric field, let's say, along the vertical direction like this, say it is making an angle theta here with the polarizing axis, then only a projection E cosine theta comes out. And if I have, say, another particular, another direction, right, let's say this direction, if I pick this direction, call it E prime, let's say E prime makes an angle theta prime with the polarizing axis, then E prime cosine theta prime comes out. And as we have seen before, intensity of light is proportional to the electric field squared, right? So if the intensity of light is I here, and let's say after polarization, let's call this I naught, and after polarization, let's call it IP, then IP is equal to I naught cosine square theta. So for electric field E, the polarization, the polarized intensity is cosine square theta, because intensity goes as electric field, and because a polarizer lets only a specific component of electric field, E cosine theta, through, the intensity would be squared of that, so it would be E squared cosine squared theta. So if I have a light, unpolarized light of intensity I0 incident on a polarizer, then the intensity of light that's coming out of the polarizer is I naught, the incident light, times cosine square theta. And again, once again, this happens because of a specific material structure, because you can create dipoles, and the oscillating dipoles re-radiate light, and because of that, essentially, you get electric field only along one specific direction. And so based on that, we can make polarizers with this. IP is equal to I naught cosine square theta. So that's what we call as a polarized light, and this law as Malice's law. Malice's law means basically that the polarized intensity is unpolarized intensity times cosine square theta, where theta is the angle between the incident light, incident electric field, and theta. Right? Okay. So with that, we basically discussed polarization, and you can have not just polarization along one particular axis. You could also have what is called as right circular polarization or left circular polarization. Because you could have, say, electric field to be just along the x-axis, or you could have it to be just along the y-axis, right? These are linear polarizations, meaning the electric field is oscillating along only one direction. But what if I make the electric field EXI plus EYJ into two different components, right? So you would have, instead of x or y, right, electric field is oscillating along both x and y. And if you look at the way these are oscillating, the way these are going up and down, you can use, for example, if you remember mechanics, where you studied simple harmonic motion or circular motion can be represented as motion along the x-axis plus motion along the y-axis. Because if I pick a particle that's going around in a circle, right, and if I pick its direction at any particular point of time, right? Let's call this r, let's call this theta. So at any time I can write r as r cosine theta along I plus r sine theta along j. So cosine theta is a component along x, sine theta is component along the y. And as the particle, let's say if you have a particle that's going around in a circle, as the particle is going around, then the net x component or the net y component, they change, they go up and down, right? They go up and down. So for example, if you start from at time t is equal to 0, if you start from x-axis, right, entire r is along x-axis and no y-axis to begin with at time t is equal to 0. And let's say after some time period t is equal to t, you would have the particle here, which would mean at time t is equal to t, the position is entirely along j and nothing along x. And in between, anywhere along this arc, the particle would have, its position would have both x and y components. And the same thing takes place in the rest of the other 3 quarters, right? So, essentially, a particle going around in a circle can be described as linear motion along x and linear motion along y. So the amplitude here is going back and down and back and forth, and here the amplitude is going back and forth. So you can have circular polarization, right? It could be right, it could be clockwise or anti-clockwise. Depending upon that, you could have right and left circular polarization in addition to just linear polarization along one specific axis. Okay, so then I briefly wanted to mention a couple of other things that are very interesting with light. One of the things is of course related to quantum mechanics. That is, we have briefly talked about the quantum nature in the first 2 chapters when we discussed de Broglie wave equation. But here I would like to mention one particular unique thing, that is when we look at electrons. We see evidence for them to behave as particles. There's evidence that shows that they behave like particles. For example, if I look at one single electron, right, I could have, please recall that I shared a video in the early lectures where we had looked at electrons in a scanning electron microscope, or SEM. We had light being field emitted from a filament, and then there were 2 slits, and then there was a screen, and we were looking at electrons on the screen, right? If you don't remember, you can just YouTube Hitachi electron double slit experiment, and you should find that video on YouTube. There, when we looked at single electrons, we saw single electrons as blips on this screen, and only after we collected, let's say, 1 million electrons, were we able to see these dark and bright fringes. Otherwise, the electrons were like particles that were popping up on the screen at one point or the other randomly, right? So although each electron looked like a particle, we were able to still describe the whole electron with a probability and wave function after several different measurements, right? And there, so something that looked like particles, the behavior was being explained using a wave function. This is called first quantization. In case of light, we don't have first quantization. In case of light, when we talk of photons, they're not on the same footing like electrons. There we basically are talking about a different quantization. We're talking about second quantization, meaning it is light still observed to exhibit a behavior that could not be completely explained using just waves. And it is it is thought of as if this light is made up of these virtual particles, like photons, for example, right? So it is not on the same footing as studying quantum mechanics of electrons, because there you have what we call as a first quantization. You see primarily particle-like behavior, and you expect the electrons to behave like particles, like for example, like a tennis ball. But it doesn't behave so. When we have taken a million measurements overall, after those million measurements, we see that basically it can be described by a wave function rather than classical mechanics of Newton, right? But in case of light, it is the other way around. You still have light as a wave, and for example, they talk about photoelectric effect. In case of photoelectric effect, it doesn't show, photoelectric effect does not show that light should consist of photons. You do not require quantum mechanics of light to explain photoelectric effect. You can still consider light as a wave and explain photoelectric effect. It doesn't require light to be quantized, right? So it is the black body radiation, for example, the black body radiation that requires light to be quantized, and we call that as second quantization. There is no first quantization for light, really. And so we think of light as if it's made of these particles, virtual particles like photons, right? And that they have a quantum of energy. So it is in that sense. So bear that in mind in the future when you are studying quantum mechanics, and if you happen to study quantum electrodynamics, bear that in mind, that what we're dealing with is second quantization of light. If you have taken quantum mechanics course already, or going to take quantum mechanics courses sometime, you will see that the second quantization is discussed when a simple harmonic oscillator is discussed. Very often, that's when the second quantization is discussed, right? Yeah. So pay attention there, and I hope you can remembering this single fact of what I told you can go a long way in before, if you have not yet taken quantum mechanics. If you have already taken quantum, then that while doing simple harmonic oscillator, you count numbers. You use this operators like A dagger A, creation and annihilation operators. Anyhow, I don't want to go too deeply into it. But another thing that I wanted to mention that is interesting about light is relativity. I mean, if we discuss light, if we have an optics course and we didn't discuss relativity, that would be very unfortunate. So I basically wanted to give you a very quick view of what relativity is, and I'll just mention this with Einstein's paper that is on the electrodynamics of moving bodies. So if you read this paper, it starts with a very, very simple question. For example, if you are on on a train platform, right? If you are on a train platform and there is a train that's coming, let's say, right? There's a train that's coming here on the track, right? It asks a simple question. Einstein asks you a simple question like, how do you know when the train has arrived, right? That means you have to first look at your watch, right? And you have to look at the train coming to this particular point, right? And you have to do this simultaneously. You have to look at the train at the same time as you look at your watch. I'm not talking about the physical implausibility of this thing, but rather think about it even more deeply. That how is there such a thing called simultaneity, right? And if there is simultaneity, then is is whatever is simultaneous for this person. For example, if this person is somehow able to simultaneously look at the train arriving at this point and the watch somehow, would those two events, that is this person looking at the train and looking at the watch, be simultaneous for someone inside the train? So what Einstein basically asked is, can you basically have a universal simultaneity? That is, if somebody is moving and somebody is stationary, is what is simultaneous for the stationary person? For example, looking at the train arriving at this point and looking at the watch may be simultaneous for this person who is stationary. But would those two events also be simultaneous for this person inside the train? So, of course, Einstein describes it in a more, he asks a more complicated question, but there is a simpler way to think about it, and that's what I'm going to quickly explain here. Let's say you're standing and you're stationary, right? And you are just stationary. And right in front of you, wherever you are, right in front of you, exactly, there is a train car, and there is another person that is standing here, exactly at the same, like right in front of you, in the center of the train car. So this person is standing right in front of you, and he is at the center of the car. Okay. Now let's say he has a switch here. He has a switch. And there is one light, let's say light to the left, and then light to the right of this person. There are two lights, and this switch is basically going to turn on those lights at the same time, let's say. Then basically, and this train car is moving. Then if you look at the light coming from the left and the right, they're at the same distance from this person in the train car. And even if this train car is moving with a constant velocity, right? And if this person inside is not moving and he stands at the center, then the left light and the right light are at the same distance. So the light emitted from the left side and the light emitted from the right side reach him at the same time. So those two events, the lights getting on after he pressed on the switch, the left right getting on and the light right getting on is simultaneous, because after this left light and the right light start glowing, it takes the same amount of time for the light from left side or right side to reach him. Even if the car is moving, they're still at the same distance, as long as the person in the middle himself is not moving within the car. So the left and right light reach him at the same time, right? So they are simultaneous for him. They're simultaneous. But if he switches on and if he is moving, nothing is instantaneous. Even the signal in this wire is not instantaneous, right? It takes some time for the switch signal to reach the left and right lights and for them to glow, right? Within that instant, this person in the train car, say, moves because of the velocity v that the person has, right? So this person would have moved in the train car. It may be a little distance, but nevertheless, the train car itself would have moved by some distance. So now the right light is farther from the person who is stationary. This is the right light, and this is the left light. Because the train car moved, because it's moving with a velocity v, the right light went farther, a little farther, and the left light came a little closer to the person who is standing. So this light would reach him faster than this light. This light reaches faster than this. It doesn't mean the speed of light is different. It means the distance this light has to travel, the right side light, is longer than the left side light. Because these lights are not at the same distance for the person who is stationary, because the lights themselves are moving with the car at a velocity v. So the left light naturally came closer and the right light went a little farther. So although for the person inside the car, the lights are at equal distance, for the person outside, the lights are not at equal distance. The right side light is closer than the left side light. So the right side light reaches him faster than the left side light. Or in other words, these two events are not simultaneous for this person. The left and right lights glowing is simultaneous for the person inside the train car because he or she is equidistant from both lights. But if the train car itself is moving, then between the time the person switches on the light and the lights glow, within that fraction of a second, the train car moves a little, however little that may be. And so the left light comes closer than the right light. And because of that, to this person who is standing on the ground, these two events are not simultaneous. And that's the beginning of special relativity. So if you look at time, what is time? Time is nothing but a duration of change. You measure time by relating two different changes, right? For example, you look at Earth's rotation, that's one motion, and you correlate it with the motion of a needle in your watch, and that gives you the time. So you're correlating two different motions, right? So like how he asks the question in the very beginning, how can you say the train arrived at this time? That means you have to look at two different changes. One is the watch and another is the train arriving at this point, right? From there, basically Einstein shows that if you have the time in the stationary frame, that is from the viewpoint of this person, is different from the person who is moving, and it is given by this equation, v squared by c squared, where v is the speed at which the train car is moving or an object is moving, and c is the speed of light, right? So it is from this point of view that the time in a moving object appears longer, right? It's from the stationary point of view that the time in a moving object appears different, because in case of the person who is inside the car, two lights glowing is essentially simultaneous event, but for the person who is stationary, those two events are not simultaneous. And this is special relativity, and this basically later led to it's not that it was a specific part of the theory, but thinking about this problem deeply led Einstein naturally to general relativity, and he named this special relativity instead of calling it extended relativity. But anyhow, that's how basically Einstein arrived at special theory of relativity. It is by looking at the electrodynamics of moving bodies. So you combine electrodynamics and the move of moving bodies with special theory of relativity, and light is essentially described by electrodynamics. Like we have seen, it's nothing but electric and magnetic fields changing in time and space, right? So that's how light and special theory of relativity are so closely linked. So I'm going to upload this part of the lecture first and then solve the problems in the next part of the lecture.